So we're going to look at this problem again so that you can see it at whatever speed you would like to see it and see another way of working this problem. So again, we've got ice and we've got steam. This ice is at 0 degrees C. This steam is at 100 degrees C. And so we're going to look at the heat needed. The first thing that we need to do when we're working this kind of a problem is to say how much energy do we have to give and how much energy do we need to absorb. And so if we think about this, the heat that's gained by the ice, if we wanted the possible heat that could be gained, would be the heat to change ice to water and the heat then to take that water up to all the way to 100 C. So when we're trying to find the state, we're really just sort of testing it. It's almost like we're working the problem backwards. We're testing out a couple of options. And then we could say how much heat might be lost. And we could say the heat for the steam to go to water. And then we might even say this water to go down to some temperature, like 0 C. It turns out that because this steam to water number is so big, we don't actually get that water cooling anywhere. But that's what we have to calculate. And so the problem steps us through sort of doing these calculations first, just to see where things are. So to do this calculation, ice to water, we just do the mass of ice times the latent heat of fusion, which is this one, right? That tells you the heat fusion and melting is the solid to liquid transition. And so that would be 0.1 times the number, so we get 3300 joules. Okay, then the heat for the water to go up to 100 C, that heat, Q, it's now water, to go from 0 C to 100 C is equal to the mass times the specific heat of water times the change in temperature. And so the mass is still 0.1 kilograms. The water, specific heat of water, is this 4,190 joules per kilogram degrees Celsius. And then this change in temperature, the final temperature is going to be 100 minus 0, and that will be in degrees C. And so when we do that, we find that this Q, water, to make this transition, is equal to then 41900 joules. Okay? So we have heat to take the water up to temperature, heat to melt the ice. So then the next thing the problem suggests is that we calculate these values. And so to take all of the steam, just to condense all the steam to water, we'd say how much mass of steam that we have times the latent heat, this time of vaporization. Oh, and the units got lost on that, joules per kilogram. So if we do that, that gives us 226,000 joules. And now we can see we don't need to make this calculation because this heat that gets lost is bigger than these two heats together. In other words, the total heat over here, Q total, is this 33 plus this 41, which is 75,200, so 75,200 joules. And we have available the possibility of 200,000 joules. So this is bigger, right? This number is bigger. And so what we can say is that we are going to be left with, because the next step for this gaining heat would be to then, for it to gain even more energy to turn into steam, which we can't do because we already have used it. We're at steam now. So what this tells us is that where we're going to end up, we will end up with a water, steam, mixture. Okay, and so what we can realize is that we can get this ice into water all the way up to 100 C. That's how much that'll take. At that point, it will be in equilibrium. It will be in thermal equilibrium with the steam. Okay, they'll both be at the same temperature. So when we get here, this takes us to a final temperature of 100 C. Over here, we have a final temperature of 100 C, even though it's steam, and so we will be in equilibrium at that point. So if we end up with water / steam mixture, then the question becomes how much water and how much steam, okay? So then we ask how much water and similarly how much steam. So we had 200 grams to start with of what was ice and steam, and if we're going to end up with a mixture, we're going to end up with some water, at least 100 grams of water, and some more, okay? And so the way we'll ask this question is we'll say Q that's absorbed, or Q in, plus my Q out is equal to 0. That's my energy conservation. And so we're going to recognize that in the Q inside we have 41900 joules plus the 33300 joules plus the question is how much steam, the unknown mass of steam, unknown steam that we need to turn, that's need to condense to then provide this amount of energy. Okay, so that's what our Q in plus Q out equation looks like. Because we know our final temperature is 100, so we know we have this, we've melted the ice, we've taken the water up to 100, so we've got that final temperature. The question is just how much steam had to translate into water to give us the energy, to take the energy out of the steam to put it into the water. And so when we set up this equation, this becomes 75200 joules plus, then we have a negative mass that's unknown times our latent heat, 2,260,000 joules per kilogram must equal 0. And the reason for this minus sign is that this is heat that's lost. Okay, usually we get the minus sign naturally in our equation Q equals mc delta T. That delta T will make it positive or negative, but when we use Q is equal to ml, we have to fix the sign. We need to set the sign. So it might be on an equation sheet, you might want to say Q is equal to plus or minus ml, and then we say plus if we're gaining, and minus if we're losing or releasing heat energy, giving it up to something else. So in this case, this is going to be a situation where we're going to have the minus sign for the lost. And when we solve this, we then have 75200 joules is equal to m times 2,260 joules per kilogram. And so now we divide both sides by this 2,260,000 joules per kilogram, and this is a good way to check that everything works because your units will work. Joules per kilogram, so the joules are going to cancel out. The kilogram is in the denominator, so it pops up to the top, and so then we find that our mass we get a mass of 0.033 kilograms, or we say that we needed 33 grams of steam into water. So our final state is a temperature final of 100 C. Mass of water at 100 C is 133 grams, and the mass of steam that we have left is going to be 100 grams minus the 33, or 67 grams. And that is our final state. So the steps here, step 1 is really, this is our step 1 right here. Step 1 is to test. See what our final state is going to be. Are we going to be in between, a water mixture in between 0 and 100, in which case the final temperature is unknown? Or do we know where we're going to get to in the final temperature and then the mass is unknown? So this is a situation where we know the final temperature. So then we have to ask the amount of mass of each. The second problem that we had, it turns out to ask a different question. Again, we don't necessarily know the final state that we're going to be looking at here. And so the question is, what's the final temperature? That's maybe an indication that we might know something about the final state, but we have to test. So we're going to do the same sort of test. So step 1 is test to see where we think we're going to be. And so what we look at is we say the heat that's needed, the heat gained for what was ice. So we start with Q ice to go from minus 5 degrees C up to 0 degrees C. Then ice to water. And then Q of what is now water up to 25 degrees C. And then on the other side, we just say Q lost, how much is available if we take all of this water sort of down to 0 C. Our guess here is that we're probably not going to freeze all of this 600 grams of water. So we're probably going to be looking at some water, and probably we're going to drop this 600 grams down to 25 C. So probably we don't have to do this piece, but we do need to see how much heat we have. Can we even turn this ice into water? So we can say what's the maximum amount of heat we can get from the water to go from 25 down to 0 C. So we'll start over there. So this would be the mass times the specific heat of water times the temperature change. So in this case, we would say, let's say we take it all the way down to 0 C. That would be the maximum we could get before it then had to start turning into ice. So 0 C minus 25 C. And notice we already get the negative sign in this. And so this becomes, this is 0.6 kilograms. And this is, because we're talking about water, 4,190 joules per kilogram degrees Celsius. So this becomes, so I get a negative. This is how much heat can be lost if I take this water all the way down to 0 C. That's the amount I have available to lose to go into this ice. So then we ask the question about the heat required to raise the temperature of the ice and to get it up to at least water state. So the heat for the ice to go from 5 to 0 is going to be the mass of the ice times C times delta T. And this temperature change is going to be, well, my final temperature is 0 C minus a negative 5 C. So that gives me a plus 5. So this is a positive change in heat because that's a heat gain. The mass of the ice is 0.05 kilograms. And the specific heat, notice we have to use ice because right now it's ice. So that is 2100 joules per kilogram degree C. And so when I calculate that, that gives me Q for ice up to 20 degrees C is equal to, putting all of these numbers in, gives me, so that gives me, when I put it in my calculator, a 525. So that's this one. And then to make the transition from ice to water, that's going to be M times my L. Remember, we have our plus or minus. In this case, we're going to take the plus because that's heat that's absorbed. And so this is just going to be 0.05 kilograms times 333,000 joules per kilogram, which is going to be 16650 joules, and that'll be a positive number. So what that says, if I add these two together, right, plus 525, that gives me 17,175 joules is the heat that's needed to take my ice to water at 0 C. And we certainly have that much that we can release over here from the water. And so what that tells me is they're going to meet somewhere in the middle. Okay? So my final state is going to be all water at some final temperature, which should be in between 25 C and 0 C. So now we finally, and we can use some of these numbers, we finally look at our Q in plus our Q out is equal to 0. And let's look at the numbers we can use. So for our Q in, that's made up of 3 terms. The Q for the ice to go to 0 degrees C, plus the Q for the ice to turn into water, to melt. So those we already have calculated, plus a Q for this ice, now water, to go to final temperature. And that's the one we don't know. So we know this for the ice to melt. We have this one. That's our orange one. That's 16,650 joules. We can reuse our numbers. For the ice to get to 0 C, that's our 525 joules. And this is going to be mass, it's now water. So now we're going to use the specific heat of water to say T final minus 0 degrees C. And then when we add our out, notice we're not taking this all the way down to 0 C, right? So we don't know. So we rewrite this for the 600 grams of water, we rewrite this as mass times C of water times T final, which is unknown, minus 25 degrees C is equal to 0. And so here again, this is 0.6 kilograms. This is 1490 joules per Kelvin degree C. And then this is our unknown right here, right? And it's in both places. And so this, just to fill in our numbers, 0.05 kilograms, and this is 4190 joules per kilogram degree C. So we're going to put all of these in. I mean, they're all in our equation now. So our equation is going to look like 525 joules plus 16,650 joules plus 0.05 kilograms times 4190 times T final minus a 0, so that's just a 0. I'll go ahead and write it out, but we know when we multiply it, it gets rid of it, plus 0.6 kilograms times 4,190 joules per kilogram degrees Celsius times our T final, that's what we're looking for, minus 25 degrees C is equal to 0. Okay, so now we put all of these terms in, we do some multiplication here, and we get the following. So if we assume that our final temperature is in Celsius, then notice each one of these has joules, so that goes away. And so we're just going to combine terms. So I need to multiply this out, I need to distribute it across and realize we've got 2,514 T final minus that, which is this 62850 plus 219.5 T final plus adding those two together gives me 17,175. All of that is equal to 0. Notice that when I add this to this, I get a negative number. That's good because we're going to take it to the right-hand side of the equation here. And then I can add these two terms. So when I add those two terms, what I get is 2723.5 T final minus 45675 is equal to 0. So I'm going to add this 45,675 to both sides, and that'll give me, finishing up this algebra, if I divide both sides now by the 2,723.5, that gives me a final temperature of 16.8 degrees C or 17 degrees C. Okay, so that I wrote out the algebra in a lot of steps just to remind you of how this algebra works. But the point here is that we tested it. We followed our steps. We tested to see what our final state was. Once we found that our final state, all water at some temperature in between these two, then what we did is step 2 is to reapply this Q in plus Q out with our unknown. Once we know our final state, our unknown here in this Q in plus Q out is going to be this final temperature. In the previous problem, the final temperature was known and our unknown was how much mass. So it's not obvious which way we have to solve this problem. It just depends on how this energy balance comes about. Okay? I find it useful, I showed you in class, to sort of do a bar chart for this. This may or may not be helpful. I'll just go over it one more time so you've got it, but hopefully. But if we look at this, I can say, here's my bar chart. The ice piece, I had ice to water. This is my 33.3 kilojoules. My water to now steam to, this is going 0 C to 100 C. This is melting. That's heat that goes in, and then I can contrast that with the heat that's available. This is probably not to scale because this is 226 kilojoules that's available. And so we can look at how much of this do we need to pull out of here. And that'll tell us, that's a way to sort of picture, this is the amount of mass of steam that needs to go into water. Well, that's the amount of heat, because I'm showing heat here. This amount of heat we need from steam into water, And from that heat, we can then find the mass, okay? So that's that picture. Over here, in the second problem, we can do the same sort of thing where we can say for our ice, so first we have a really small amount, the 525 joules. That's to get ice to 0C. And then we had this amount to melt it, to melt. And then over here, we had sort of quite a bit more. So this would be available from water to go all the way to 0C. But since we're at a point where water doesn't get all the way to 0C because these two don't take up all of this, right? These two, I'll make that purple, take up only a portion of that. What that tells us is that our temperature is going to be somewhere in between. And so what our real drawing is going to look like is going to be this small amount, this bigger amount. And then what we've got to do is sort of balance the extra here so that this is water to final temperature, so that it matches the amount, so that these three together equal this water to our final temperature, right? So basically we adjust the height of this green bar, how much final temperature, as this goes up, right, then this goes down. And so what our equation is doing is matching those two so that we still get this equaling to that once we get to our final. And so these two circled things are what became our equation of Q in plus Q out is equal to 0 once again because we had that balance.